Well done. Let's do some exercise, and we'll start with this one. We have something like this. So like a cross, but it's a rhombo arrangement. We have positive Q here, another positive Q here, and then negative Q here and negative Q here of the same value. And we have this sort of arrangement where this and this makes a rhombo type, and this angle is 60, and we know that the distance between this middle point and here is A, and also this is A, right? Now we want to demonstrate that the electrical force, okay, on either of these two minus Q is 0. So how do we do it? How do we demonstrate it? Well, let's take this point here. We have an electrical force between 1, 2, 3, 4, between 1 and 4, which is attractive. So we have this force F14 in this direction. We have this force in this other direction, F12. And they are the same because they are generated by Q plus, which in modulus Q it's the same as Q minus, same quantity, right? And then we have we have the force between this Q, which are negative, and therefore the force between the two, it's a repulsion, and this is F13. Okay, so we can see immediately from the drawing that if we take a coordinate system x, y, like that, we see that this component of F12 along x, and this component of F14 again along x, when they sum, they are 0. The sum of the two is 0. So we can write that F14 along x, it's equal to F12 along x, because these two charges in 4 and 2 have the same value, Q plus, and this charge is Q minus. So these two forces, F14 and F12, are actually the same, but in different direction. Now we have, if these two kind of cancel each other, because of this reason, we are left with the vertical component. And this one is the vertical component of F14 along y, and this one is F12 along y. Alright, so all we have to care about is the component of the three forces along the y direction, because the other two along the x direction, they cancel each other out. Right? So to do the equilibrium along the y direction, we have to evaluate how much are these forces. So we have to also know how much is this distance. So we know this, the angle is 60. If you want to calculate this x here, okay, x is an unknown, it's not this x, an unknown. How do we calculate it? But tangent of 60, the tangent of this angle it's equal to a divided by x, right? And therefore x is equal to what? It's equal to a divided by tangent of 60. And how much is tangent of 60? So 1 divided tangent of 60 makes 0.58. So 0.58 a. So we calculate x, this one, from the middle of the rhombo to this place here to 1, we have 0.58 multiplied by a, which is this length. Very good. Now F14, which is the same in modules to F12, this is the module. How much is it? It's 1 over 4 pi epsilon 0 multiplied by what? By Q14, this and this, but it's Q squared, divided by the distance. How much is this distance? Well, that distance we can calculate it with the sine of 60. It's equal a divided by L. Let's call this L, and therefore L is equal a divided by sine of the sine of 60, which is 1 divided sine of 60 makes 1.15 a, right? So we calculate also this length. Here we put 1.15 square multiplied by a square. And how much is F13? F13, it's equal to 1 over 4 pi epsilon 0 multiplied by QQ squared divided the distance. So it's 2 times x, 2 times this. So 0.58 by 2 makes 1.16. So 1.16 the power of 2 a squared. All right. So now we have calculated these forces along this direction. So we have to calculate the forces in y direction. So the forces in y direction, it's this cosine this angle, cosine of 60. So F14 y, it's F14 cosine 60. But how much is cosine 60? It's 0.5, eh? Cosine 60, you see, 0.5. So this one is 0.5 F14. And the same F12 in y direction, it's how much? It's F12, but it's F14 cosine 60. So again, 0.5 F14. So when we sum these two, okay, we get F14 in y direction plus F12 in y direction, it's equal to F14. But F14 is this. Therefore, if we make the F13 plus, well, not plus, minus, because F13 is along the positive sign of y, whereas 1, 2, and 1, 4 point downwards. Okay, so minus the sum, it's F14. F14. And how much is it? Let's look at it. F13 is this. 1 over 4 pi epsilon 0 q square divided by 1.16 square a square minus this 1.4 pi epsilon 0 q square divided by 1.15 square a square. But look at that. They are, the same. This factor is the same as this, q square, and then, a square, and this number, it's an approximation. The reason why it's a bit different because of the approximation we made in calculating sine, cosine, tangent, but these are the same, so the sum, it's actually 0. So this, as well as this, they don't actually move. They don't have any force attached to it. And if you do the same for q plus and this of the q plus, you will find something rather weird too. And I suggest you do this now and you put the comments in the video what you find out. So you just calculate the same kind of force distribution for the q plus here and this q plus here and see what you get in terms of forces. Okay, well done. Let's move and do another exercise. In this other exercise we have two charges like this and and this. So they are charge Q, they're both positive. And then you have another charge which makes a circle around this axis. So this kind of circle, it's perpendicular to this line. I've drawn like this, but it's perpendicular to this line. It's like going around like this. Okay, this is my finger, my thumb, it's along that axis, and the other fingers go around this circle. Okay, so this charge, it's negative and it's going around this circle. And what we want to do is we have this Q, this 2Q are 5 the power of minus 6 Coulomb. Then the length between this point 0 and here, it's L. And L, it's 6 centimeter. This is also L from here to here. Good. Then this charge here, okay, has is minus and it's Q prime. Q prime, it's minus 4 power of minus 6 Coulomb. And the mass of Q prime, it's 9 microgram. Microgram means 10 at the power of minus 6 gram. It's something minuscule. It's really small, So we see this small q prime going around and making one complete turn in 1 kilohertz. So the frequency, okay, of this circular motion, it's 1 kilohertz. 1 kilohertz is 1,000 hertz. Okay, so it makes 1,000 turns in 1 second. Very good. So we want to calculate the total force that these two exert on this charge here. What is the total force? Well, what we do is we redraw this like this with points, okay, and then we take this here, okay. Now in this exercise we did not consider the weight of this charge. Even if we are given the mass, we don't consider the weight, otherwise there should be a weight of this small charge, okay, with the small mass. So we don't consider that. So when we just consider the electrical forces, this is positive, this is negative, therefore on this small charge here there is a force like that, okay. We call this one 1, this 2, this 3, position 3. So between 1 and 3 we have this force 1 F13, and the same force but in the direction between 2 and 2 is exacted by this Q on Q prime, and the force is F23. All right. Now, so what happens, okay, to this, okay, we have two forces plus we have another force. These electrical forces have to be considered also with the centrifugal force, due to the fact that this is Q prime is moving around in a circle, okay. So if it's moving around in a circle, the acceleration AC, centrifugal acceleration, it's along this direction, and the centrifugal force, okay, it's like that, it's opposite to the apparent acceleration. So this is F centrifugal. All right. Now we have these three forces. We see that two of them, 1, 3 and 2, 3, you know, they are symmetrical compared to this vertical line. If they are symmetrical and they have the same modulus, then we don't have to consider the x components. If we take, you know, this, we have, and we put x, y axis, then, you know, this component of F13 along x and this component of, you know, F23 along x, they are the same, but they are pointing in different direction. Therefore, you know, the sum of them is 0. So we have to add just this component, the vertical component of F13 vertical or y, and this one is F23 in y. So what happens is that F13 in modulus, which is equal to F23 in modulus, it's equal to what? It's equal to 1 over 4 pi epsilon 0, then q prime divided by the distance. So is this distance. How much is this distance? We don't know. Okay, this distance is r. We know L. So this distance, how much is it? We call it, you know, h, for instance. How much is h? Well, h, it's equal to L square plus R square and square root. So it's the square root of L square plus R square. But, you know, we know L, we don't know R. Yes, that's true, but we know that this thing, Q prime, goes around with a frequency, with this frequency. So, how much is the FC? Fc of acceleration, it's equal to what? The force, the centrifugal forces, it's m q prime multiplied by AC. But how much is AC? M q prime multiplied by v squared over r. Alright? Good. But we can write this also this way. mq prime multiplied by omega square r. Now, omega is connected to the frequency. Why? Omega is equal to pi frequency. Because we have the frequency, 2 pi multiplied by 1,000, 2 pi multiplied by 1,000, which is the frequency, it's 6280 radians per second. This is omega. Alright? So here we have mq prime, which is 9 micro G. So it's 9 micrograms. 9 micrograms, 9 and the power of minus 6 grams. In kilograms, it's minus 9. So this is not 6, but it's 9. Okay? Because we wanted everything in kilogram. So microgram means power of minus 6 grams. In kilograms, minus 9. Because there are 3 more places between grams and kilograms. 9 at the power of 9 multiplied by 10 at the power of minus 9. This is the MQL. Very good. Now, we need to multiply by this squared. So 6,280 squared. Plus, multiply by r. What r? We don't know yet. So which kind of number we get here? 9 power of minus 9, it's equal, it's multiplied by 6280 square, it's equal to 0.35 r. Okay, so we calculate this. Now, if we go back here, we need to put inside here this length, h. So it is, L square plus r square. Because h should be squared here. So h squared is L squared plus r squared. Great. So here we have the 2q. So we have the 2q, we can calculate this part of the relationship. 4 multiplied by pi multiplied by 8.85 at the power of minus 12 multiplied by q, 5 at the power of minus 6 multiplied by this of the q, 4 at the power of minus 6. So we calculate this part, which is 2.22 10 at the power of minus 21 divided by L square plus R square. In reality, we know L, but let's leave it like this, okay? Now, if everything it's kept, in the same position, moving in the same position, it means that, these forces Fc, F13 and F23 must be, the sum of them must be 0. Otherwise, this small charge will move. Okay? So if we sum them up, what do we get? Well, we have 2 components along the y direction. Okay? So what do we need to do? Well, we need to sum them up. So we have, F1 3 over y and F2 3 over y. There are 2. Right? So we have, that F 2 times F1 3 over y. How much is it? Well, we can take this angle, for instance. Okay, this angle here, how much is it? Well, this angle, it's alpha, for instance, and tangent of alpha, it's equal to L divided by R. Okay, and then if you want to calculate this component of F13, we use this angle. So F13 is directed along H, capital H. So we have capital H or F13 and then cosine of alpha, and we get the component along the y direction. So we get, you know, that this one, it's 2 times multiply F13 cosine of alpha. Okay, F13 is this. So we have, you know, 2 multiply 2.22 power of minus 21 divided by L square plus R square multiplied by cosine of alpha. And at this point, okay, we can't say that this is equal to FC. So we can do the equilibrium at this point. So FC is equal to 2 times F13y. So we have this plus this in this direction, it's equal to FC in this direction. So we have, you know, made the equilibrium. So FC, how much is FC? FC, it's here. So FC is 0.35 multiplied by R. And 2 times, oh, sorry. This one, how much is it? Let's do the 2 times, so it's 444 10 to the power of minus 21 divided by L square plus R square cosine of alpha. Okay, but cosine of alpha, how much is it? Cosine of alpha here, cosine of this angle, it's R divided by H. So it's R divided by H. But how much is H? Is this. So this is R divided by square root L square plus R square. Okay, folks, now that we arrived here, the rest of the solution of this is left to you. You know, it's about, you know, mathematical operation. You know, you just have to solve it for R. Okay, you solve it for R and you get how much is R, and then you can once you get this R, then you can calculate all the forces that are involved. You can calculate how much is the centrifugal forces, okay, and how much is, you know, these 2 forces that, you know, pull the charge Q prime in 2 different directions with the same module, you know, and yeah, that's how you solve it, you know. Benissimo ragazzi, facciamo un altro esercizio, ok, per questo capitolo. Abbiamo un manubrio ed è fatto così. Abbiamo una barra, qui ci sono 2 sferette A e B, e Q con A qui è diversa da Q con B che sta qui. Okay? Questo manubrio è come, per esempio, è sospeso, no? Il manubrio è sospeso al punto medio da un filo, quindi è come se avessi questo, guardate, io ho preso questo righello, vedete, è sospeso, no? Con una corda, guardate, sospeso alla metà, quindi sta sospeso così, ecco, non ci sta sospeso, ecco, sospeso così, benissimo, e agli estremi ha delle cariche fisse, benissimo. Ora mettiamo vicino delle altre cariche, una carica qui ad una distanza, no? Che è DAC, questa è la carica nel punto C, carica Q con C, e poi un'altra carica qui nel punto D, e chiamiamo carica Q con D, dove questa distanza qui è dBd. Ok? Allora andiamo a definire tutte queste lunghezze. Questa lunghezza qui, L, è uguale alla lunghezza del manubrio, è uguale a 42 cm, quindi 0,42 metri. Poi Q con A è uguale a 14 nanocoulomb. Nanocoulomb vuol dire 10 alla meno 9 coulomb. Poi Q con B è uguale a meno 3 nanocoulomb. Poi abbiamo Q con C che è uguale a 61 nanocoulomb e Q con D è uguale a meno 55 nanocoulomb. Benissimo. Poi abbiamo le distanze DAC che è uguale a 5,4 cm, quindi facciamo in metri 0,054 metri, e DBD è uguale a 2,7 cm, cioè 0,027 metri. Benissimo. Ora dobbiamo calcolare il momento totale delle forze esercitate sul manubrio rispetto al centro del manubrio. Quindi dobbiamo fare il momento di tutte le forze rispetto a questo punto. Allora, vediamo subito che la forza esercitata elettrica esercitata tra B ed A passa proprio per il centro del manubrio. In qualunque posizione il manubrio si trova. Così, in qualunque posizione il manubrio si trova, la forza elettrica tra A e B passa per il centro di rotazione del manubrio, no? Quindi non c'è alcun momento. Bene. Ora, la forza tra Q con A e Q con C quant'è? Ecco, Q con A e Q con C sono tutte e due positive, quindi è una forza repulsiva, cioè va in questo senso. Quindi questa è la forza FAC. E che succede tra la forza B e D? Tra B e D, guardate, sono tutte e due negative, quindi pure questa repulsiva, ok? È lungo questa direzione repulsiva, è F, la chiamiamo FBD. Ora, ci sono pure altre forze, no? Ecco, se io considero questa carica qui, ecco, questa carica qui esercita pure una forza con la carica in B, quindi Q con C e Q con B, tra questi due c'è una forza elettrica, tra C e B c'è una forza elettrica, e c'è pure una forza elettrica tra D ed A, ok? Tra D ed A c'è pure una forza elettrica. E c'è pure una forza elettrica tra C e D. Quindi qua di forze elettriche ce ne stanno parecchie. Ok? Ecco, andiamo a fare un grafico, no? Per capire meglio, perché qui ci abbiamo messo altre informazioni. Andiamo a fare il grafico soltanto delle forze, no? Con i punti. Ecco, qui. Ora facciamo un grafico, diciamo, in scala. Ecco, se questo è 42, ora questa distanza qui tra C e D è questo 42 cm, ecco, questo deve essere 5 cm, quindi è per esempio qui, ok? Ecco, e l'altra è ancora più vicina, qua. Il punto medio intorno al quale facciamo il momento è questo. Allora, la prima forza F con AC è diretta proprio così, ok? F con AC. Quindi il momento di questa forza, momento di AC rispetto a 0, quando è uguale? È uguale a FAC per la metà di L, quindi per L mezzo. E come gira? Gira in senso antiorario, quindi è negativo il momento. Poi c'è il momento della forza BD. Il momento della forza BD a quando è uguale? MBD è uguale alla forza FBD per il braccio, che è un'altra volta L mezzi. E come gira? Gira pure nel senso antiorario, quindi è negativo. Cioè nel senso orario, scusate, è nel senso orario. Guarda, tutte e due girano nel senso orario. Quindi tutte e due sono negative, perché noi assumiamo come positivo il girare nel senso antiorario rispetto a un punto. Quindi questi due momenti sono tutti e due negativi. Ora veniamo alle altre due, no? Alle altre due cariche e le forze che esse generano per essere in quelle posizioni. Quindi abbiamo detto c'è la forza tra C e B. Ecco, la forza tra C e B, ecco, C è magari qua, questo è C, no? Questo è A, questo è B e questo è D. Ecco, la forza tra C e D e B, come passa? Cioè passa molto vicino, ok, a 0, veramente molto vicino. Cerchiamo di fare un disegno, ecco questo qua. Quindi guardate, ci passa veramente vicino, ok? È la stessa cosa per la forza tra D e C, cioè, qua si passa su 0, ok? E che succede tra A e D? È un'altra cosa che passa molto vicino a 0, ecco. Per cui il momento di queste forze può essere trascurato perché il braccio rispetto a 0 è molto piccolo. Quindi F con CB per il braccio, che chiamo così, è molto vicino a 0. Può essere, o meglio, può essere trascurato rispetto a queste altre. La stessa cosa per F di AD è la stessa cosa per F di CD, okay? Proprio per costruzione, okay? Quindi questi momenti, questo lo chiamo braccio con 1, braccio con 2 e braccio con 3, ecco, sono tutti trascurabili rispetto a questi due. Possiamo non trascurarli. Quindi il momento totale è la somma di questi due, quindi è uguale a F di AC per L mezzi più FBD per L mezzi. Ora dovete calcolarvi naturalmente le forze, no? E quindi le forze F con AC a che è uguale? È uguale a 1/4 π greco epsilon con 0 per Q con A per Q con C. Quindi ce l'abbiamo, no? Q con A e Q con C. Diviso, ecco, la distanza tra A e C. La distanza tra A e C è DAC. Quindi DAC al quadrato. Poi abbiamo F di BD è uguale a 1 diviso 4 π greco epsilon 0 per Q con B per Q con D diviso questa distanza qui, quindi D al quadrato. Una volta calcolate queste, li mettiamo qua dentro, moltiplicandole per L mezzi abbiamo trovato il momento. Ecco. Questo cercate di finirlo voi, magari quello che potete fare è rendervi conto di questo. Quindi io vi consiglierei di fare una costruzione proprio su carta, non so, millimetrata, la carta a quadretti di un vostro quaderno, ecco, per rendervi conto, no? Misurandoli proprio quando sono questi bracci, e per vedere che in effetti questi momenti, il contributo di queste forze al momento totale è trascurabile rispetto a questi due, perché questi due sono posti a distanze ragguardevoli rispetto al centro. Se li paragoniamo alle altre forze, va bene? Benissimo. E con questo abbiamo finito pure gli esercizi di questo capitolo che tratta della forza elettrica. Grazie mille.